Hello guys, this is CodeNCode and this is video editorial or the lecture in which we are going to study how we can build Centroid decomposition tree. Till now we have seen only the theoretical part of Centroid decomposition. In this lecture we are going to code some parts of it. In this lecture basically we'll be studying how Centroid decomposition tree is built and what is the algorithm to do so. Of course we are going to use DFS, so I'm assuming that you are well aware of those algorithms. I'm assuming you are well aware of DFS as well as recursion, because of course when you are learning this level of algorithm, you are supposed to have knowledge of at least recursion and DFS and similar algorithms which are very easy to understand, which are basic algorithms to get started with graph algorithms or graph theory. So since this is one of the advanced topics of graph theory, I'm assuming you already know how graph works, the representation of it, the DFS, recursion, and so on. So let's see how we build Centroid decomposition tree for this tree. Now, if you remember from the previous lecture how we build a Centroid decomposition tree, I mean how we choose a centroid for a given tree. Now for a given tree, the centroid is chosen in that way that whenever you choose certain node as centroid, and when you remove that node, the connected component that are formed, the different connected components that are formed, none of them has size greater than n by 2, where n is the size of the overall tree. Now for this, as you may already know, 1 is the centroid of it, because if you remove 1 from this tree, it would create 3 different disjoint components, and none of them have size greater than n by 2. For example, this and these three will be formed as a result of removing this node, and none of them will have size greater than n by 2, and so those will be this will be the centroid. This is a valid centroid. So how we actually code it and how we get the work done using the code. So to remind which node is actually the centroid, first thing we do is we need to know which, when you remove certain node, we would run a DFS and check for each node whether this can be a centroid or not. If certain node is centroid, then none of that node's subtree will have size greater than n by 2. So first thing we need to do is root the tree, because currently we do not have any root. So we would select certain node as root and calculate subtree size of each node. So this is the subtree size of each node. I'm assuming node 2 to be root. Node 2 to be root. So node 2 is root. So this subtree has size 1, this subtree has size 3, and this subtree has size 10 for node 2. Similarly, this subtree has size 5, this has 2, and so on. So assuming node 2 to be root, we have calculated the subtree size of each node. Now what is the step 2? Step 2 is to find the actual centroid. So we would start from root again. Now we need 2 DFS. First, to calculate subtree size of each node. Let me show you the code. This is DFS1. So this subarray will keep the subtree size of each node. This will keep the information of centroid decomposition tree. This is important. And this is an array of set for adjacency list representation of the graph. Now if you are following the graph theory series part 1 and 2, you already know that till now we have been using vector of int, but here we are using set to represent the adjacency list representation of graph. The reason is because when you are working with centroid decomposition, you actually need to remove certain edges. When you are removing edges in vector, it will require O of n time, that is linear time, but here in set you can do that. Removal of edge or removal of any node from the adjacency list of certain node can be done in log n time, because set supports insertion and deletion in log n time. That is why I'm using set, not vector of int. So here you see I have DFS1 part which will calculate subtree size of each node. As you can see, we have already seen this code many times in in other algorithms, so I'm not going into details much. So what I'm doing here, so initially of course you would initialize the subtree size to be 1, and then for each node in the subtree for each node in the adjacency list of current node, if the adjacent node is not parent, that means it's children, so we would make DFS call to that node passing the current node as its parent, and of course it would return the size of the subtree rooted at node adj, and that would be added to current node subtree size, and finally we would return the subtree size of current node. So this is basically, this DFS is calculating the subtree size of each node. So we will have two different DFSs for different needs. First is to calculate subtree size of each node. So we are assuming node 2 to be root, and we have calculated subtree size of each node. Now step 2. Now in step 2 we would again make a DFS call starting from the root, and in this DFS we would find the actual centroid. Now if 2 was the centroid, then none of its subtree would have size greater than n by 2, right? So this subtree is not having size greater than n by 2, this because n is 15, so of course n by 2 is 7. This subtree is not having size greater than 7, this subtree is not having size greater than 7, but this subtree is having size greater than 7, which is n by 2. So of course if you choose this node as centroid, this would be an invalid selection, so this cannot be a centroid. Now here's a question for you. Pause the video and think, where should you move to? Where do you think, in which subtree you can find the centroid, the valid centroid? Will it be in this subtree, will it be in this subtree, or will it be in the subtree which is having more than n by 2 nodes? So the answer is, you would find centroid in those subtree which is having more than n by 2 nodes. Why? See, you need to move towards that so that you can reduce the subtree size of this which is having more than n by 2. If you move away from it, basically if you move here or here, the subtree size will remain intact, and you won't be able to find a valid centroid because this would still be having subtree size greater than n by 2. So you need to move towards that which subtree is having more than n by 2 number of nodes. So that is why from here we would make DFS call to here. As soon let me just show you. So from here I moved on to here. Now here I don't have to look back to this, because first of all, when you are making DFS call and this is root and you came to here, of course this is not your subtree. Your subtree is only this and this, because that is your parents, so these are your siblings and so on. So you don't have to look back, only you have to look inside your subtree. Now we are on node 1. We would see for our subtree whether any subtree of us is having more than n by 2 number of nodes. So we will see for 4 is having only 5 nodes, 3 is having only 3 nodes, which means none of the subtree of node 1 is having more than n by 2 number of nodes. That means node 1 is valid choice for centroid, and hence we would return 1. So what is happening here? 1 is chosen to be the centroid. So what is happening here? See, first when you need to find the subtree, the centroid, what you would do, you would make a DFS call to certain node, assuming it is the root. So I assume node 2 to be root and made a DFS call to that to calculate subtree size of each node. After that, here's the centroid. Let me show you from the main function. Inside the main function you can see reading n, the number of nodes, and then n minus 1 edges, each time reading each edge and inserting in the adjacency list of x, inserting y. Similarly for y, inserting x. Now I'm asking to decompose the tree rooted at 1. Here I am rooting at 1, but here in this example I was rooting on node 2. So since I was rooting at node 2, so I would pass 2. Now since 2 would be the centroid of all of the tree, so this would not have any parent of it, so as a parent I'm passing minus 1. After that, this is the decomposition. This is P, the parent, and this is the node. Basically this is the root of the tree you want to decompose. Initially we would pass 2 because we want to decompose this tree, and we are assuming 2 is the parent of it, the root of it. So first of all, what we would be calculating, we would be calculating subtree size of each node. That is why passing the node as the root, we are calculating subtree size of each node. And you remember, this is DFS1, which calculates subtree size of each node. After that, it returns, of course, the subtree size rooted at this node. And since this is the root of the entire tree, so it would return the overall size of the tree. So basically, if you make a DFS1 call to node 2 for this tree, it would return 15, because that is the subtree size of node 2, or any root you choose for the overall tree. So this is the subtree size. After that, what you do, you are making a DFS call. Now this DFS, which actually finds the centroid for you. So how it goes, you pass the root, you pass the parent of it. So of course, when we were to find centroid for this tree, root would be 2 and parent of 2 would be -1. Parent is being passed as p, and p is passed from main as -1. So for the main root, it is passed as -1, because for each centroid it has to report its for example, if this was the central server, it would decompose them into sub countries. Remember from the previous lecture, then you would find the centroid of this subtree, and that would report to the central server. So basically, central server will act as parent of all of the centroid which is created by this. Basically, you choose this as centroid and remove all of these 3 edges, so it forms 3 new sub countries, and each sub country has a new centroid, and that is because this removed certain edges, and those would report to it. So this would act basically as their parent. So that is why you need to pass parent as well. So basically, the central server will not have any parent above it, because it does not does not report to anything. That is why we are passing -1 here. So what you do, you take the root, pass the parent, and also the subtree size. Why do you need to pass the subtree size? See, when I want to decompose this whole tree, I need to know which node is valid centroid choice. A node is valid centroid choice if none of the subtree of that node is having size greater than n by 2. What is n? N is the size of the whole tree, and that is why you need to pass the size of the whole tree as well. That is why you are passing subtree size, and subtree size is actually the size of the whole tree rooted at this node. So basically, you are passing n, you are passing parent, and you are passing the node, and that would return, this DFS would return the centroid. And how is that happening? So basically, how DFS works, this DFS, so it takes node, p, and n, the size of the tree. So in the adjacency list of current node, it would check for each subtree if adjacent node is not parent, because of course you only need to check for your subtree, not the parent. So if it is actually your subtree, it is root of actual subtree of you. For example, if you were at node say 1, so 4 and 3 are actually representing the subtree, while 2 does not, because 2 is actually parent of 1. So 4, we would only check for 4 and 3. So if adj is not p and subtree size of adj is greater than n by 2, if the subtree size of certain subtree is having more than n by 2 number of nodes, what you would do, of course you move towards that, right? See, from here we would check for this subtree. This was having less than n by 2, lesser equals to n by 2. This subtree was having less than n equal to n by 2 number of nodes, but this subtree was having more than n by 2. So what we did, we moved from here to here, and that is what exactly happening here. If certain subtree is having more than n by 2, then we would make recursive call to that subtree, because the centroid would be inside that subtree somewhere. So that is why we are making DFS call, recursive DFS call to that subtree, passing the current node as its parent, and of course the subtree size won't change. And if for each node in the subtree of current node, if none of the node in the subtree of current node is having more than n by 2 number of nodes inside its subtree, you would reach this, which means none of the subtree is having more than n by 2 number of nodes, which means the current node itself is the centroid, and that is why we are returning node, the current node. And this is how the this DFS which finds the centroid works. So this DFS calculates the subtree size of each node so that we can use that knowledge to calculate the centroid, and after finding centroid it will return the centroid. So that is why when you make a DFS call, of course when you make a DFS call you get the centroid, so this represents centroid. Now these are only print statement to show you, to make you believe that okay, we are working fine. After that, what you do, you need to set the parent of centroid, or basically the node to which this centroid has to report. So let me show you what is happening. After calculating subtree size, after calculating this, we made DFS call to DFS function. First we made DFS1 call, so we have calculated subtree size of each node, and then we made DFS call that returns node 1. So that is why we are having node 1. Node 1 points to no one because we have passed -1 as parent of it. So node 1 points to no one because this is centroid of whole tree, so it do not have to report to anyone else. What I'm talking about here, I have already explained in the previous lecture, so make sure you have watched the previous lecture. Now when you find the centroid of it, what you would do, of course this centroid would remove all of the edges and would create new subcountries, right? And those subcountries will have their own centroid, and those centroid will report to this, right? That is why this would act as parent of those new centroids. So what it would do, it would remove edges one by one and find their centroid. So it removed this edge. In the adjacency list of node 1 we were having this and this 3 edges, so it removed this edge and then would make a recursive call to find centroid of this subcountry. So what is happening here, once you have found the centroid, for now just ignore this line. What you are doing here, in the adjacency list of centroid, each node in the adjacency list of centroid will form a different connected component or different subcity, or sorry, different subcountry, right? So what you are doing in the adjacency list of the centroid, you are removing this in the adjacency list of that node you are removing centroid because the edges are bidirectional. So in the adjacency list of 2 there is 1, and in the adjacency list there is 2, so we need to remove 1 from the adjacency list of 2 so that when we make DFS call to this, it is not able to jump here, because in the adjacency list of 2 there won't be 1. If there is no one in the adjacency list of 2 and you are making DFS call to any node here, it won't be able to jump here. That is why we are removing the centroid from the adjacency list of that node, and then we would find the centroid of that node, I mean of the subcountry which is rooted at that node. So that is why we are making decompose call to that node, passing the current node current centroid as its parent. So what is happening here, I have removed the edge because of the erase, if you can see in the code, and then I would find the recursively I'll find the centroid of this subtree or subgraph, whatever you can, I mean whatever you want to say this. Now if you see, the centroid of this subcountry would be 5. So 5 is the centroid of this subcountry, and this have to report to 1, right? So parent of 5 would be 1, so parent of 5 is 1, and that is why when we make a decompose call to certain node, we also pass the parent, and centroid would be the parent of it. That is why we are passing centroid. So this is how the code works. So now as you can see how this code works, let me show you once again the overall procedure. So what happens, whenever you want to decompose certain tree, you pass certain node from that tree, considering that it is a single tree, it is not a forest. That means there is only a single connected component. Basically, if you want to decompose certain connected component like this, you can pass any node from this in the decompose function, and it will decompose that into a centroid decomposition. Now what is happening here, initially I'm passing 1 to decompose the whole tree, assuming node 1 is the root. So what it would do, first it would calculate the subtree size of each node, then it would calculate the centroid. After finding the centroid one by one, it would erase the edges and then recursively decompose the newly made connected component as well. So basically recursively it will keep decomposing until it reaches a single node. From there it would return, because if there is only a single node, you don't need to decompose it. And since the decomposition only, for example, after decomposing this, now this becomes the centroid, and now it would one by one find the centroid of other connected component, which are made by deleting one by one edges of this node. So I've deleted this edge, and now it would find the centroid of this connected component, but this is a single node, so this is centroid of itself. And since this is what made this connected component, so centroid of this would report to node 5. That is why the parent of 6 is 5, and that is why we are using this parent array. So basically for each node we would have their parents. If I show you one more example from the article that I have asked you to read from, Tanu's article on centroid decomposition, here you can see this is the overall tree which we want to decompose. So this is its centroid decomposition. Node 8 is the central server, and then it decomposes the whole tree in two parts, this and this. Now the for this connected component, centroid would become 2, and from this connected component, centroid would be 9. So both of them will uh, report to node 8, or basically parent of 2 and 9 would be 8. And similarly for these 4, parent would be 2, and for these 2, parent would be 9. Similarly for the 7 5 would be 6, because 6 is what decomposes 7 and 5. If I show you this by running the code that we have wrote, this is the input for this tree. So let me show you real quick. So here you see tree now tree rooted at 1 with size 15. So tree rooted at 1, on this root, this is the whole tree, right? And so the size is 15 and centroid found is 8. So this is the first centroid found for the whole tree. Now this would decompose the whole tree in two parts, this and this. So this, either it would make recursive call to this to find centroid decomposition or centroid of this subtree, or it would make call to this. So now we have made call to node 5. So after removing this edge, we have made call to this node to find centroid of it. So as you can see, this has found this has size 7. As you can see, 4 and 3 7, and centroid found is 2. So you can see for this subtree, centroid is 2. So the parent of 2 is 8. So this is how the centroid decomposition works. So till now we have only decomposed the tree, and we have set the parent of each node. So here you see, just a second, this. So see, parent of 1 is 2, as you can see, and parent of 2 is 8, parent of 3 is 2, parent of 5 is 6, where's 5? So here it is, and so on. Parent of 8 is -1, because 8 is the central node, central server. It doesn't have any parent. And I'll be providing this code so that you can run and understand the working of this code. And each time when you decompose this, like, just a second, when we erase this edge and we wanted to find the centroid of this particular subtree, what we did, we would calculate the subtree size of each node again, assuming this node to be its parent, the node which was directly connected to the previously found centroid. So each time we would calculate, as you can see, whenever we are going to decompose again and again, whenever you are calling decompose function, it again and again calculates the subtree size, and again finds the centroid of that subtree. So this is how this building centroid decomposition works. I'll also be providing the code so that you can understand this and you can play with it whatever you want. So this was all for this lecture. If you have any doubt or query or suggestion, of course you can post it down in the comment section. So thank you guys for watching, and soon I'll be posting the update and query part, how the update and the query part of Centroid decomposition is handled. So thank you guys for watching. Until the next video drops, keep coding. Thank you.